understand the dynamic response, such as what is the damping factor and what is the time response. For example, if it is step response, how will it behave? Will it behave with some oscillation come back to the new step value, or will it behave like a step value and it just grows exponentially and unstable system? And these are the things which we can understand from the root locus. Or it behaves like a totally undamped system. For example, if you have have roots on the Laplace plane right on the imaginary axis, so then the behavior, for example, this is a new step value and the system will respond here and it will start oscillating without any damping. So now we have to understand today about how to draw the root locus of a dynamic system. So let me go ahead and start the root locus. My objective is to explain the root locus, and the equation of a root locus is this one. The denominator of the transfer function, this is a transfer function, okay? This is a closed loop transfer function. The denominator, which is 1 plus gh, it is equal to 0, and that gives us the root locus equation. And what is the angle of this gh? So the angle over here is, this is also known as the root locus equation. We have two types of criteria: magnitude criteria, where the absolute value equals to 1. G is the forward transfer function and H is the feedback transfer function. And the what is the angle criteria? Angle criteria is the angle of -1 means 180 degrees, and it is the odd multiple. So 2k plus 1 is the odd multiple of plus minus 180. Like you can go from positive real axis counterclockwise, which is plus, and positive real axis counterclockwise, which is negative. So it's negative. So this angle is 180 plus, this angle is 180 degree negative. And k values goes from 0, 1, 2, dot, dot, dot. So GH is a transfer function. You, if H equals to 1, that means unity feedback transfer function or a control system. And if the G is K over here is none of the gain value, what happens to the poles of the characteristic equation? These are the poles when you change the gain from 0 to infinity, and where do the poles go? And today we will start an example here. Let us begin with an example in our book. Consider the system shown for in this figure. So let me show you this figure here, 10-41. The question is where we draw the root locus. First of all, sketch the root locus plot and determine the value of gain k such that the damping ratio of the dominant complex conjugate closed loop poles is 0.5. So let us draw the root locus. So we know that the angle criteria equals to plus minus 180 2k plus 1. And let us start. So when you first of all I will draw the real and imaginary axis. The real axis is x-axis and imaginary axis like y-axis. And then I will plot these poles, the denominator. So where are the poles located? S1, uh, one factor is s equals to 0. Other from the other factor s equals to -1. Third pole is located as -2 on the real axis. So from the characteristic equation, from the, the denominator, you have to find out the roots of the denominator, which are the poles or open loop poles of the transfer function. But you will start from the open loop poles and then you will tweak the gain. So let's start marking s equals to 0, s equals to -1, and then keeps on moving forward. More space. So let me change this to here. So these are the locations of the of three poles. So let's test. Let's put a test pole here. So I will just put a test pole here, not 0, but a test pole. I will say a test pole here and see the angle from here to here for each pole. What is the angle? So S star, it's 0. What is angle of 0? It is 0 degree. Pole 2 minus S star. And for pole 3 is again 0. Do you think it's fulfilling the criteria? Our angle criteria says that the angle of the test pole to the all angle, the summation of all the angles, so that would be equal to 0 degree. 0 is not equal to 180 plus minus. So this means all this side is not included in our root locus. So then you can select this side. What is the angle from here to here? Is 180. 180. From here to here it is 0. From here to here it is 0. So it is 180. So I would say this side, let me change the color. So color to show you the real axis. If the test pole is located between the two poles, this is the poles root locus will lie on this thing. So let's test this area. This area, is this area included in our test pole, the root locus or no? So look, what is the angle from this pole to this test pole? So this test pole is located here. Is look, is 180 degrees. So I'm gonna show you 180 degree for the first pole, and from here to here is 180 degree, and from here to here angle is 0. So is 2 times 180 degree, which is not equal to the odd multiple of 180. You see, so this region is also not included in our root locus, because we can see that one. Now I'm going to show you with another color to show you the third region, which is away from the last pole. So look over here, I want to test this region. So look over here, from here to here, 180 degree, plus from here to here, 180 degree, plus from here to here is complete 180 degree. So three times. So for the test pole at third location, it is three times the 180-degree counterclockwise. So this location, all this location is inside our root locus on the real axis. So we have proved it. But I want to show you a easy way. You don't have to go through very complex way. The one which I have learned, very easy way. You don't have to do any math. So look over here. First you draw the let me take over here. First you draw the open loop poles on the real axis. Okay, this is my transfer function. G is our transfer function, and these are the open loop poles. So you always start from the open loop poles, and then tweak the gain. So look, this is my imaginary, this is also known as the Laplace plane or real and imaginary axis. And now look, first you look at the first pole, which is s equals to 0, second pole s equals to -1, third pole s equals to -2. So the easiest way, let me change the easiest way is to draw the root locus is to do the when you drag the pen, you don't have to drag the pen until you drag your pen when when you touch the first pole, when uh, odd pole or zero comes on real axis. It is not the real axis, it is not the case for the imaginary axis. Okay, so look, what is the odd? This is odd, this is even, this is odd. So drag the pen down when you see odd until you hit the next pole. You lift the pen up and then drag it down. When you see the odd pole or zero, you could drag it down all the way here. So you see, it's the same root locus which we found through the math, and which we are finding through the graphical representation. You drag your pen when hit odd number of poles, or zero. It doesn't matter. Zeros are the numerator roots of S. You understand that? So we will see more examples, and in this case the number of poles which are equal to 3, and number of zeros which are 0, and m represents the number of zeros. Zeros are the numerator roots, and n represents the number of poles. Agreed? So we have currently 3 poles. Look, these are the 3 roots of the denominator, and no 0. Agreed? Now what we have to do, find out where will they leave this axis, because poles can never, when we tweak the gain, poles can never intersect. They will always depart the real axis. One will go up, other will go down. This up movement and downward movement is complex conjugate, the pair of complex. How does it travel? Let me show you the way So what is this centroid? This is known as the sigma, uh, location of centroid asymptotes. What are the asymptotes? So sigma a is the location of asymptotes, or also known as a centroid, because the pole, when you tweak the gain, when this gain k goes from 0 to infinity, then at the open loop poles location the gain is 0, and the infinity, and when gain equals 0, infinity, then it reaches to the open loop zeros. Right now we don't have zeros, so it goes to infinity. So but how do you draw the angle of the asymptote? So please write down the angle of asymptote. So first of all, where is the location? Location is, the formula is all the summation of all the poles minus summation of all the zeros divided by n minus m. Number of poles are, in our case, 0, -1, -2, and there is no zero, so minus 0 divided by n minus 1, and minus m is 3, so -3 over 3, it is -1. So the location of asymptote is right over here. This is asymptotes will depart. Now what angle they will depart from? So there is another formula. How would the centroid, the asymptotes will, the angle of the asymptotes, I would say angle of asymptotes, the angle of asymptotes equals to plus minus 180 2k plus 1 whole divided by n minus m. So when k equals to 1, so let's say k equals to 0. What is the angle? Theta 1, and it always gives you two angles. Each value of k gives you two angle possibility, and then it starts repeating. When you add k1, k2, they start repeating on the same line. So I will show you. Let's k equals to 0. So what is 180 divided by 3 plus minus 60? And what is plus minus 60 in our trig identity? So in our angle here, suppose this is my angle here. So this is my asymptote is 60 minus 60. You don't have to draw this axis right now. This is like sigma a. Agreed? We need one more angle, because how many asymptotes we have? Asymptotes are equal to n minus m, number of asymptotes, not sigma, but sorry, number of asymptotes. You see my point? Asymptotes equals to n minus m. So we need three lines. One is plus 6. So let's do k equals to 1. In that case, we will have another two angles. So plus minus 180 divided by 3 times 3. Agreed? 3 is cancelled by 3. So plus minus 180, that line is starting from here, plus is going here. So this angle, this angle. So plus 180, negative 180. So you see guys, so these are the three lines. The first asymptote is this one, second asymptote is this one, third asymptote is this one. So our root locus, the loci of all the points will travel along these three asymptotes. That's our guidelines, I would say, our system. And we will see where the system become unstable, how much is the gain that the system. So let me show you this again. This real axis and imaginary axis, these are actually the Laplace plane. The real axis is positive. So I'm gonna show you the first pole here, second pole here, third pole here, and then location of sigma a is also located here. So I'm gonna draw a line here at 60 degree, a line here at 60 degree, plus 60 minus 60, and then I need to draw it one line here at one. So these are the three asymptotes. Agreed? Now, what is the breakaway point? So breakaway point is the point where the two poles, when they start moving towards each other, then they break the real axis apart. One goes up towards the uh, uh, positive side, one goes down towards the negative side. You see my point? So you, whenever, remember, whenever it touches the enters the right half plane, whenever the root, even one root of the pole touch, or one pole moves into the right half plane, system becomes, the response becomes exponential, um, exponentially growing positively, which is never, like, it's unstable. So we don't want our poles to pass this imaginary line, this j omega d, and this real axis also known as a sigma or zeta omega, and this is the, these are abbreviations. So these, whenever it passes through the imaginary line system, we don't want that. The system becomes unstable. You see my point? The response becomes exponentially increasing. It does not come to the mean position. We want to keep in our poles in the uh, left half plane. So let me show you. The left half plane is our desired plane for stability of our system. Now let me show you what is this breakaway point. We also call it as a breakaway point, or the location where the break the real axis. So this is our equation of the characteristic equation of our transfer function. And then what is g? K over s plus 1 s plus 2. Agreed? And from here, if you do the manipulate rearrangement, everything is k equals to negative s plus 1 s plus 2. So I can write here, if you multiply all these, do you get this negative? So this is my k. Now, in order to find the breakaway point, you have to differentiate this k with respect to s and equate it to 0. And let's do this. So when you differentiate it, I'm sorry, this is there is little error here. So let me show you what error I made here. I think, can you multiply this again? Uh, I think I did derivative first. So let me show you. Can you do the multiplication? Is it s cubed plus 3s square plus 2s? Yes. One student verifies this is my k. So now let's do the equated to, so let's find out what is my uh, differential of k with respect to s. So let's do the derivative. Dk over ds equals to, negative sign goes to the right hand, so becomes 0, so don't worry about negative. So 3s square plus 6s plus 2 equals to 0. Agreed? Now from this you can find out the roots of this equation. So s1 equals to negative 0.42. You can verify in your calculator. S2 equals to negative 1.57. Now guys, look, this is my first pole, this is my second pole, this is my third pole, and the answer is, this is one answer, second. So you see this is neglected because this region is not included in our real axis. So this is neglected. So we have to consider this location, which is negative 0.42. This is the location where the roots will depart, and this is the location of the poles asymptotes. You see my point, guys? How did I find the breakaway point? You have to use the equation of the characteristic equation. The denominator of the closed loop transfer function is also known as the characteristic equation, and equate it to 0, and then from there you can find out k value, which and then differentiate it with respect to s. That gives you the location of the breakaway point. Now guys, when how will you find out the location of this is important, j omega d. Don't worry about d right now, just say what is it. So now in this equation, so let me grab this equation here. If you bring everything to the left hand side and equate it to 0, that will be, so k, I would say, like, let's write down like this: s cubed plus 3s squared plus 2s plus k equals to 0. Now this is the characteristic equation, and also known as the root locus equation. And now you plug in, since we want to find out the location of this point, and the response over here is undamped response. So you see, undamped, no damping. So if you see over here, the poles are located here. This is known as the unstable system. It keeps on growing up and up. And if the poles are located somewhere here, the response will be going up, and a very nice response. It comes to the mean position, which is stable position. You agree with your professor? Now let's find out this location. Let me explain to you. Before I find this, I want to explain you one thing. If you say this is the equation, and you want to find out what is the gain value over here, so you will tell me, professor, when you plug in x equals to negative 0.42, can you plug in negative 0.42 plus k? And from here, what is our gain value? Let's do it together. So this is negative. It means when it goes to the right hand side, this becomes positive. Do you verify this? One student says yes. So the gain value, this is point. Okay, my pen is a little bit having difficulty. So look, this is the gain value at the location, on this location where this breakaway point is. So if you understood this easiest example, this was the easiest example where you can find out the gain value, and now you have to find out the gain value at this location. What is the gain value at this location? So again, you will do the same process. You will take this equation. Let me show you. You will take this characteristic equation and replace s by wherever you want to find out the gain value. So now we want to find out the at j omega. You see my point? So can you plug in at j? So let me replace s equals, plug in s equals to j omega. So that will give me the location of gain value over here where s equals to j omega. So let's do this. Let's plug it in over here. And how are you going to find it out? Look, j omega cube plus 3 j omega square plus 2 j omega plus k. Now, in this case, equation, we have two parts. One is the real part, one is the imaginary part. So let make sure you understand that j square equals to negative 1. So can I write down here j cube or negative j? Can I write down negative j omega cubed? Agreed? This one is because j square is negative 1 times j becomes negative j omega. Over here, this is negative 3 omega square. Agreed? Now this one remains like this. It will not change. Now in this case, you will separate j part and real part. So and equate them to 0. So what is the j part here? Negative omega cubed plus 2j omega. Agreed? Equated to 0. Other part is also k minus 3 omega square. Now guys, from this part, what is omega? Take omega common. I'm sorry, I made a mistake. It should not have two j in it because this is just the component of j, not the j value. You understand me? It's the coefficient of j. And now what is left here? So it is equal to 0. So omega, either omega equals 0, which means it is at rest, which means it is at rest. And or the second part is omega square equals to 2 and omega equals to plus minus square root 2. And now you plug in over here. You omega equals to square root 2. Plug in over here because it's 3 times 2. Because square root 2 square is 2, so you get 6. So gain value at the imaginary axis is what? It is equal to 6. You see my point? How you find out the gain value on the imaginary plane, imaginary axis. Now I want to show you one picture which helps you to understand more about the real axis and imaginary axis here. So let me show you here that picture here. The real axis is actually zeta omega n. So if I have a location over here, the coordinate of this location is negative zeta omega n plus j omega d. Now guys, if beta, cosine beta is adjacent over hypotenuse, that means zeta equals to cosine beta. And beta, if beta is equal to what is beta equals to cosine inverse zeta. So now in our case zeta is how much? The question states zeta equals to, I believe it was here, when poles are zeta damping ratio zeta equals to 0.5. So let me change it to 0.5 and find out the angle. So beta equals to cosine inverse, it's 60 degree plus, I would say plus minus 60 degree. So what you guys have to do here, you have to draw the root locus and draw a line. So if you draw a line in the MATLAB, the command for the root locus is R LOCUS is the This is the command or locus of the transfer function. Suppose this is my root locus, and then you draw a line at 60 degree. As you see, this beta is angle located here. Agreed? So it's 60 degree here. So what is this location? And then you have to understand some right angle triangle form. So right angle, you have to draw. Let me zoom this portion here. Let me zoom it over here. So you have to draw a right angle triangle. So what is the location of, so suppose this is my S sub D, which is the dominant pole location. Okay, the poles which are close to the origin, they are dominant poles. The poles which are away from the origin or imaginary line, it is non-dominant pole. They will have less effect on the time response. So let's see, the dominant pole location is here. So what is this? So imagine, so I'm going to show you, this is my j-axis. So can I write down like this, x and jy? Let's write down y here. So can I write down like S, desired pole location is x plus jy, and then what is the angle at tangent 60 here? What is tangent 60 here? Y over x. So can I write down y as square root 3 times x? So now can I write down like this, s plus x plus square root 3x times j? Now I have successfully replaced the pole with only one variable. So that is the pole which you will put in the characteristic equation. Try to understand me. What I did in the plane is little bit tough. It's not tough that much. You have to do some right angle triangle technique. Okay, you replace y by another x, so we will have two x's in the desired pole, and then though that pole you will enter in this characteristic equation to find out the x value. Once you find out the x value, you can multiply by square root 3 to find out the y value, and the desired location of the pole will be written like this. So let's do this math here. So the way I'm going to show you, I'm going to s by s sub d, which is equal to x plus square root 3. Agreed? So now what I have to do, I have to do again the same technique, x plus square root 3 times xj, this is j by the way, and plus 3x plus square root 3 times x j. I forgot j here. Okay, this is my j. I should have written here again so that you should not get confused later down the road. So this is my j. Agreed? And now I will leave it to you one thing. You have to open the parenthesis here and then equate the real part and the imaginary part like the way I did over here. Separate them, equate them to 0, and find out omega from one part and plug it in the second part to find out the gain value. And the answer for this one, I'm skipping some steps here, but x equals to 0.33, and the desired pole location is negative point. You agree with your profile? And at that location, look, at that location, this is my root locus. At that location, what is the zeta value? Zeta value is 0.5. This is my desired pole location, that if I have this gain value, you can also find out the gain value at that location, which is from this same equation. Do you understand how do I explain the root locus? So let's do one more problem. So before I go to the next problem, have you understood how to find out the root locus, how to find out the gain value at a certain pole? I have shown you three examples. One is the real axis. You just take the plug in the value, like you see x domain and plug in x equal x value is 0.5 1 2 and find out the new value at that. So it's the same thing you have been doing in from college algebra you studied. So it's the same thing but a little bit a real and imaginary axis. So let's do one more problem to understand. This is example. So you have to draw the root locus. So draw the root locus for this unity feedback control system and the gain value with the damping factor of 0.5. It is not the dumping factor but the damping factor, okay? But it's the same question, but I have changed the transfer function. So I'm going to show you very quickly. One root is located at 0. The other two roots are so 2 and 3. The other two roots are this as located -3. Agreed? So 0, -3, and -3. There are double poles at the same location. So here is number of zeros are 0, number of poles are 3. And sigma equals to number of poles, summation of poles minus summation of zeros divided by n minus this is 3. Okay, in our case this is -3 divided by, so our location of the centroid is this -2. Agreed? So now our what is the angle? So you see, first of all let's do the pen test. So first I'm gonna show you, I'm gonna change the color here. I'm gonna bring the pen here. As soon as I hit the first odd number of poles or 0, I'll bring the pen down and go up until even number. And even number hits at the same location where the odd number is. Agreed? So I will move the pen down and then bring it here. Okay guys, have you understood how did I draw the real axis root locus? And now I want to find out where is the breakaway point. So I need to show you the equation of the root locus. So which is 1 plus gh equals to 0. And g is how much? G equals to this value. Okay, this is my g. Look, I'm gonna plug it over here. So 1 plus k over s times s plus 3 whole square. So if you bring it on the right hand side, this becomes equal k equals to negative s cubed plus 6x square. And then differentiate it with respect to s and equate it to 0. That means that will give us the location of the breakaway point. That will give you, so I'm going to write down here. So 2s square, sorry, 3s square, 12s plus 9. So the location equals to -1 and -3. Agreed? Let me double check it in my calculator. Can you check the roots are correct? Yes, you found it. They are correct, right? I'm unable to open my calculator here. So let me show you. The next thing is to find out the root locus. So one root will leave this axis here, and there is a break in point. I'm sorry. What am I doing here? This is not the correct answer. I have to draw the angle of asymptote. So look over here. The angle of asymptotes is 60 degree. Agreed? So I would take this point at -1. One pole will start. This pole will start moving here to the left. There are two poles. One pole will go to the right. Other pole will go to the left. Do you understand that? Another thing I want to mention here, that from this equation, I will say, how do you find out the system whether it's stable or unstable? So let me show you another concept here, the Routh's stability criteria. This is the characteristic equation. So how are you going to apply the stability criteria? Routh's. So what you have to do, all the largest degree of s, and then smaller, and then smaller, and then smaller. So the coefficient of s cube is 1, coefficient of s square is 6, and then go to the next column here, and the coefficient of next smaller s is 9, and then you're left with constant here. And the way you do the math here, the next row you will be completing by multiplying these two diagonal elements. 6 times 9 is 54, minus off diagonal element, which is k, divided by this number, and put 0 over here, and then for you will do the same. You multiply these two diagonal elements and minus this. 6 times 0 is 0, so you and divide by this number. You see my point? So when you multiply and divide by the same number, you are left with k. So make sure in the Rouse stability criteria says that you should not have any sign change in the first column. You see my point? If you see some sign change, it means one root is lying in the right half plane, which is this unstable system. You see my point, guys? So can you tell me? So let's make this value. This is positive. So can you make it like 54 minus k over 6 is positive, and this is also this last row gives you positive value. So from here, what do you guys get? From here, you get k is less than 54 but greater than 0. So can I write down k ranges from 0 to 54? I would say is goes from 0 here and 0 here, where the location of the pole is a gain value is so the location of is k equals to 54. As soon as it moves away from the imaginary line, system becomes unstable. And you can tell your professor that what is the omega value here by using the same criteria. So have you understood how did I find out the root locus and the breakaway point? So one more thing you can write down here, that the angle of departure and angle of arrival. So angle of departure is 180 plus the angle of GH. Angle of arrival is 180 degree minus angle of GA. So for example, if you have holes located here inside the plane, so how would you leave the, which angle do you leave? So you will use this formula to see what is the angle. Suppose this is the angle of departure here. So this is the angle of departure. And if they arrive over here, suppose these are the location of the zeros, open loop zero. So you will draw just a reference plane here and see if the angle of arrival coming from here is suppose 120. So it will go like this, 120. You see my point here? It will go the same mirror image. You see my point, guys? So the angle of arrival is found using this formula. Angle of departure is found using this formula. So I'm going to share with you some examples which you will do at home and test yourself whether you understand them or not. So with that, I'm going to end this lecture. Thank you for attending the lecture.